Hey, ChemStars, this is Mrs. Vandeweghe bringing you Chapter 4, Section 3, the electron configuration of the atom. This is where we're going to start, last section. And Miss Macaulay left off 4.2 with the Schrodinger model. And again, Schrodinger improved the Bohr model, saying that no longer these electrons orbit the nucleus in these circular paths, but instead they have these sphericals and peanut and daisy and flower orbitals that all merge together so that the electrons are as optimally far away from each other as they can possibly be so they can all coexist, okay? So this is how what we understand the electrons and the atoms here today. This is the most recent model. And some proof that Schrodinger was right was that it matches the periodic table so well, okay? And so the periodic table that Mendeleev put together in 1867 is matching up perfectly what Schrodinger said, in the 30s, wasn't it? And it verifies each other's, contributions, if you will. So if you recall, the S, or the tall two columns on the left, what does that mean? Those electrons, 1 and 2 and 3 and 4 and 11 and 12, are zooming around the spherical pathway. What about P? Well, boron and carbon, their electrons are zooming around what I call a peanut-looking shell. The middle section, the transition metals, are the D, which I call the daisies. They're this four-lobed, looks like a flower in a sense, or a daisy anyway. And then down at the bottom is your F, and those are your 8-lobed flowers. Okay, Mrs. Vandeweghe came up with sphere, peanut, daisies, and flowers. That's not their official names. And honestly, this SP, D, and F all goes back once again to that line spectrum, the thing that we saw the first day in this unit when we looked at the flame tests and the line emissions. What they discovered is that when you're looking closely at some of those larger elements like mercury or something, that they have different thicknesses of their lines. And so that's where the S, P, D, and F stands for. The S is your sharp lines, all right? Your P is are your next thinner line. Those are your principal lines. And then some of your thinner lines would be the diffuse lines, and the thinnest lines would be the fundamental. So a sharp, principal, diffuse, and fundamental is really where the SP, D, and F terminology came from. But Mrs. Vandeweghe calls it sphere, peanut, daisy, and flower, okay? Because I think that helps with the visualization of what these orbitals really look like. Notice I put something else down the side. I put 1, 2, 3, 4, 5, 6, 7 on this left-hand side here. And why would I have done that? Well, let's go back a few pages and let me show you why I did that. Do you remember this picture? You remember our n equals 1, n equals 2, all the way up to 7? That's no coincidence, all right? Like I said, the periodic table really verifies everything we've been talking about. And these 1, 2, 3, 4, 5, 6, 7 now relate to 1, 2, 3, 4, 5, 6, 7. So right now, this is not a more recent periodic table. We have a 118 up here. So an element 119 comes, it's going to be right here. And we will then have an 8 shell, all right? So these are what we'd call energy shells or energy levels. And if you want to be exact, the cerium starts with 6 and thorium starts with 7, all right? So it's a continuation of 6 and 7. What do you mean? Well, look at the periodic table. This is 57 and hafnium is 72. Well, where are the missing elements? They're all right here. They kind of like get folded into these areas right here, okay? Well, now what we're going to do is something called the electron configuration and orbital notation. When we talk about bonding, and bonding will happen, we'll start talking about in chapter 6. It is very, very important we know where these electrons of these atoms are, all right? Where are they located? Because that will then determine which electrons are available to bond with and which ones are not, all right? So the purpose of what we are doing right now is to kind of give an address, if you will, for each and every electron that's found in the atom. Why do we need to know their address? So we know which ones are available, which ones are, quote, home, to bond, and which ones are buried deep inside of these orbitals, if you will, and they are unavailable to bond, all right? So that's the purpose of this next section, all right? So that's what this is, electron arrangement in the atoms. So we're going to construct orbital diagrams and electron configurations. We're going to show you a shortcut, that's your noble gas notation, to show you the location electrons, why. So again, we know which ones are going to be used for bonding. And we're going to do this for the first 3 periods, okay? And probably maybe a few beyond. How's that? Now, there are some rules for all of this, okay? And electron configuration, again, is the ways in which electrons are arranged and giving them addresses. So our rules are, the first one is the Aufbau principle. If you know anything about German, that word Aufbau means to build up. All right, so the build up principle. And what does that mean? Electrons are going to occupy the lowest, or the energy, or the orbitals of lowest energy first. Let's scroll back up again. So they're going to start with orbitals 1, and once it's filled up, then orbitals 2. Once it's filled up, then orbitals 3. Okay, that's your Aufbau. So once we start filling them, we go to the next. Then there's something called the Pauli exclusion principle. An orbital can hold at the most 2 electrons, and that's because of their spins. Electrons in the same energy will the same spin first until it's added to the orbital, then will spin in the opposite direction. And so if you have a spinning electron, that'd be an electromagnet. And if you know anything about the King's Island, the Flight of Fear, you're sitting on the car in 1 minute, and next thing you know, you're zooming off to the ride. How does those carts get the propulsion energy, if you will, to zoom off out of there that fast? Well, they use electromagnets. Electromagnets are spinning coils of electricity. And they have found that if you have coils or spinning electrons, you're going to create a magnetic field. So if you turn on that switch, you have like a switch in the car and the switch, in the holding room, that if you have them going in opposite spins, all right, they will be attracted to each other. But if you have them going in the same spin, they're going to be repelling each other. And then, the one cart will zoom off then. So the idea is spinning electrons, if they're spinning the same way, they will repel. If they're spinning in opposite ways, they can attract, okay? It's your electromagnetism. So that's why we're saying electrons in the same energy will have the same spin until another one is added to that orbital. So these are different locations. These are different orbitals. These are different rooms. So they're spinning in the same direction because they're in different rooms. These are in different rooms, so they can spin the same direction. But how do I get that 4th electron in the 2p energy level? You're going to put it down. Why? So that it spins in the opposite direction of the first one, so they can coexist, okay? And finally, we have something called Hund's rule. If multiple orbitals have the same energy, 1 electron goes in each of them before they start to double up. And this is kind of showing it too. So this one, these are all in the same 2p energy level. So this one gets its own room, this one gets its own room, this one gets its own room, but when I get my 4th, 5th, and 6th electron, they have to double up, okay? So that is your basic rules. Let's go on to the next page. So orbital notation is a visual, all right? And what you saw on that prior page of the arrows going up and down, that's an orbital notation. So the arrows represent the electrons, the dashes represents the physical orbitals they are located in. And they're represented by a line, and they're labeled with the energy level 1, 2, 3 and the subletter SPDRF. So let's go back and see what we just, and arrows are used to represent the electrons, all right? So let's go back to the last page. So this would be a partial orbital notation. So each arrow represents an electron. Notice I have the 2p right here. So what does that mean? Well, let's go back up to my periodic table. So here's my 2. Over here's my p. Well, how many are there? There are 6 going across, right? Well, if each orbital can hold up to 2, and I have 6 of them, I need 3 orbitals, don't I? There are 3 p orbitals, 3 different peanut looking orbitals. Let me show you. So I have 3 lines here, all right, and because I have 3 p orbitals. So when I have a 2p here, again, that means I'm up here at the second energy level and I'm over here where the p's are. So I'm talking about boron with the first electron going up, carbon with the second electron going up, nitrogen with the third electron going up, oxygen is where it comes back down again. So here I have boron's electron, carbon's electron, nitrogen's electron, and the one going down is oxygen. So what if I wanted, oh, let's just say fluorine? I'd put it going down. What if I wanted, oh, let's say neon? I would put it down. All right, that's your orbital notation. Now let's go back to the next page. So electron configuration is the number of electrons in a sublevel is indicated by adding a what? Highlight that, a superscript to the sublevel designation. So hydrogen is 1s1, helium is 1s2, lithium is 1s2, 2s1. Let's kind of go back to that periodic table again. So hydrogen is 1s, and it's the first electron. So that 1 is a superscript, tells you how many electrons are in that. Notice I did put helium over here where it should be for doing this. I know helium's over here in your periodic table, but for doing electron configuration, you need to put it over here. So if you haven't done so already, put helium there. So helium is in the first energy level. It's in the S, so it's in a spherical path, and there's 2 of them. So you put the superscript 2. Look at lithium. Well, it's electron number 3, right? So what does that mean? 1 and 2 have already been used up in the first shell. I filled it up. So remember what we said about right here, that Hund's rule? If multiple orbitals have this, oops, wrong one, must be, oh, here we go, off-ball, silly me. Electrons occupy the orbitals of lowest energy first, silly Mrs. Vandoy. So anyway, once 1s has been filled up, then it goes to 2s. Once 2s is filled up, it goes to 2p. Once 2p is filled up, follow the periodic table. 3s, then what? 3p, then what? 4s, and then what? 3D. I'll tell you about that later, okay? Here's another visual that might help you. Look at this. What goes first? This is Hund's rule. 1s, then 2s, then 2p, then 3s, then 3p, then what? 4s. And remember I told you about 3D? Why does 3D go here? Because 4s is a lower energy level than 3D. Then what? 4p, then 5s, etc., etc. Some folks think this is helpful. I personally don't, but we're offering this to you. So if you follow the arrows, 1s, 2s, 2p, then 3s, follow the arrows, then 3p, then 4s, then what? 3d, then 4p, then what? 5s, and it goes that way. I don't like that. I like looking at the periodic table and knowing what it tells me, okay? So I'm actually going to stop here, and you're probably saying, thank goodness. And this is a great place, all right, that we're going to be practicing the first 3 periods, okay? So we have another handout we're going to do in class, and so I'll quit here. So don't wait to be great. We'll see you next time, and I hope this helps. Bye-bye.